So here's an example of a group, an abelian group. Why don't we do an abelian group? The simplest abelian group is the integers. So that's the, 0 plus or minus 1 plus or minus 2 plus or minus 3. Positive and negative integers, denoted by a bold-faced Z here. So the product operation in the integers is addition. A plus B. That's the product operation. That's clearly associative. When you add three things, it doesn't make any difference which order you do the adding. What's the identity element for addition in the group Z? It's kind of stupid. 0, exactly. The identity element is 0. If you add 0 to A, you always get A. What's the inverse element? What is A inverse? Minus A. So if you take the negative number, that's why we have negative numbers, really, to turn counting numbers into a group, if you think of it. Well, what is minus 3? It's the thing you add to 3 to get 0. Okay? And, well, that does it. So this is a very simple group, which has the property that A plus B is B plus A. So groups like this, of course, were studied before there was a notion of a group. I'll tell you a funny story. So Don said when he recalled his algebra course from MIT, he was so confused the whole time he took the course, but he learned how to do it because he was a very good mathematician. He said that his idea of a group, as he got out of this course, was that a group was the integers. All groups were the integers. Except that somehow when you were doing the problems, you weren't allowed to use the fact that A plus B was B plus A. And he thought that this was very strange, and it was a strange way to teach, but if those were the rules of higher mathematics, he would go with it. So I want to point out that sometimes you are allowed to use the rules that A plus B is B plus A, when it holds. Another example of a group is any vector space. That's a group because you just forget about the scalar multiplication. The addition, the binary operation is addition of vectors. The identity element is the 0 vector. Right? You add the 0 vector to any vector, you get the vector back. The inverse element is the negative vector. Okay, so you just forget scalar multiplication. So it turns out that once you come up with this rather simple definition, there are groups all over the place. This is also an abelian group.